Hello everyone, and thank you for coming to my talk. My name is Scher, and I'll present the work I have done with my collaborators from MIT, Sadra, Sadraddini, and Russ, Tedrake, and my PhD advisor Hadas, Kress-Gazit. In this work, we developed a method to efficiently verify systems with stochasticity against signal temporal logic specifications. Let's dive right in. If we want to deploy robotic systems out in the wild, we must formally guarantee that they are safe and that they'll do their job, especially in safety-critical applications. Of course, verifying on real hardware is impractical. We cannot test enough possible scenarios, it takes too long, and the cost of failures is too high. In this presentation, we'll show you how we can verify, meaning finding the probability that some dynamical system with noise is satisfying signal temporal logic specifications, STL. It will be extremely useful when the probabilities are low. Take, for example, this illustration. An autonomous car needs to drive to the campsite with some timing constraints, such as reaching before sunset, while avoiding obstacles such as trees and people. This is captured by the STL specification phi. The car controls depend on some sensors like Lidars or cameras, which can have noise and would affect the trajectories. Some obstacle may also move around with some uncertainty, so there are lots of ways that this system can play out, and we'd like to evaluate all the probability of satisfying this task. Disclaimer, I may use fail or satisfy interchangeably throughout this talk because we can always put a negation sign in front of the entire specification to change between them. Now this is a hard task. One of the most promising ways to solve this problem is by running Monte-Carlo simulations to evaluate the probability of failures. It is very attractive because it applies to nonlinear systems, complicated noise models, even black box systems. But generating independent samples from an arbitrary distribution on high dimension space, and we're also usually talking about finding rare events, makes it difficult and requires lots of simulations, which is expensive. The idea in these papers shown here is that the sampling distribution is refined through the course of simulating sample trajectories to encourage collisions. This would consequently reduce the number of required samples. In practice, we do not know where we need to get useful values, especially when having a complicated underlying population. One more thing, we're talking about verifying the system with respect to some specification. And there are lots of ways to fail it, and all of those must be considered and sampled. Jumping to the end, our approach will be addressing these issues with less samples. I mentioned that we were dealing with STL specifications, so I'll give a brief introduction to what is STL. STL is an extension to temporal logic, where the propositions are essentially extended to predicates over real values and real time. An example is shown here, where the specification states that always if and when the robot hits an obstacle implies that the robot eventually needs to get to the repair dock within 3 time units. So the predicates mu are just some real valued function h over the state x, and it gets a true value if it is positive. Here we consider only affine predicates, and that's important for later. The syntax of STL is shown here. It is defined recursively, and there are Boolean propositions, predicates mu, psi are STL formulas, which can be compositions of other formulas. We have negations, ands, and time untills. From this, we can also construct other temporal operators, such as time eventually and always. Why do we use this to create specifications for systems? Well, first, we can imagine that it is easy to specify complex behaviors that we want our system to follow. It also makes sense to form the physical constraints as predicates. Third reason is that it has a robustness metric. With it, we do not only know whether the specification is satisfied or not, true or false, we also have a real valued measure of how close it is to failing. Now we can formally state the problem we're trying to solve. We are given a discrete time system, not limited to this form shown. The process and the measurement noises are either Gaussians or Gaussian mixtures. We are also given a specification, for example, the following reach avoid tap specification, which is pretty standard in robotic navigation scenarios. We want to evaluate the probability that the system satisfies that specification. On the right, we can see just an example of what this all means for a robot in a 2D environment. We can see the satisfying trajectory on the top, and the 2 others are failing, one by colliding with an obstacle and the other by not reaching the goal on time. Before we dive into the details of the solution, I just want to give you a bird's eye view of the approach. Going back to our rolling example, and due to the noise and all environmental effects, we'll start by obtaining a representation of the possible trajectories as a Gaussian in high dimensions, the trajectory space. The trajectory space is a stacking of all of the states of the time-discretized trajectory. This is why our dimensions is getting pretty big. Then we'll create the linearly constrained regions for the relevant parts of the problem, like obstacles, goals, etc. Then, using the specification, we are going to project these predicates onto the trajectory to create the trajectory level constraints. This has to do with the timings symbolized by these clocks and other Boolean relationships. Finally, we evaluate the probability of failure by integrating the trajectory level Gaussian under these domains. Remember, xtraj is a point now in high dimensions that represent a trajectory. Generally, these integrals do not have any analytical solution. We are going to base our method on this Markov Chain Monte-Carlo technique, MCMC, presented in this paper by Gessner, integrating over Gaussians under linear domain constraints. The technique is combining the HDR algorithm to evaluate even very low probabilities using the product of conditional probabilities shown here on the left, and the elliptical slice sampling, ESS, as a mechanism to sample rejection-free and parameter-free in the HDR process. The samples come from a Gaussian distribution are within some linear constraint domain. In our case, the domain will represent a region in trajectory space where all trajectory points within it are, let's say, failing. This sampling is done efficiently because the intersections between the domain's hyperplanes and the auxiliary ellipse created here on the right has analytical solutions, and they can then sample a point within that domain. Now let's look how it might look like for a Ricci-Voigt type specification in our rolling example. The straightforward way to take advantage of the framework I just presented is to create the linear constraint domains in the trajectory space, all of the possible ways that the system satisfies the specification. We extend the original paper by allowing sampling from multiple constraint domains simultaneously, rejection-free, and efficiently, even if those are under a small probability mass. By working with full trajectories and by allowing sampling from a union of domains at the same time, we can intuitively see why we are not double counting as some methods like chance constraints do. If an active segment is overlapped by two or more domains, it means that they are dependent and correlated, but it will only sample from those once. I want to mention at this point that once we have all the setup in place, we can efficiently sample never before seen trajectories with the ESS. If you think about it, it's pretty cool, because you can create new trajectories that satisfy the STL specifications and the dynamics at the same time. This could be useful for analysis and synthesis. However, this can be done with only selected scenarios. The problem is the exponential blow-up of enumerating all of the possible combinations that satisfy the specification. We need to find all of the possible combinations that the trajectory may be valid and integrate them. Another example that is hard to enumerate is when we have untils in the specification. In a generic specification, enumerating these domains is at times impractical. So what can we do? The challenge is how we can enumerate all of the regions that satisfy a generic specification. What do those domains even look like? This slide is the main nugget of the paper. The first key observation is the fact that all of the places on the ellipse that the trajectory changes from in or out of the domain are when one of the hyperplanes forming some predicate intersects it. It doesn't have to change its status, but if it does, it will only be in an intersection. The second key observation is that instead of creating all the linear domains, we can exploit the STL robustness metric to compute whether a trajectory satisfies the specification or not, positive or negative. The STL robustness metric value itself will guide the sampling by helping deflating the regions in the HDR phase. We can do this by defining the respective domain in the HDR, L, using the row level set of the robustness. So what we'll do is take all of the individual hyperplanes from the state level predicates and smear them through time like so, without even considering what's going on inside the specification. We get all of the possible intersections analytically. Not all will touch the ellipse, but that is okay. We then evaluate the robustness metric of the specification on a single point within each segment. Since the robustness is continuous, it is guaranteed that it will not change its sign within that segment. Thus, we have found a way to compute the integral and obtain the active segments without ever seeing how the domains look like and without even ever enumerating them. We have reduced the complexity of evaluating the exponential number of domains where the specification is satisfied to a matter of solving hyperplane ellipse intersections in the order of t times n. We can evaluate the probability of all satisfying trajectories without ever enumerating them, and for rare events by sampling from the posterior distribution in a rejection-free and efficient manner. Let's see an example with an STL formula where a holonomic robot must visit a small goal in bold within 0.25 seconds from reaching the big goal in the light green, and of course avoid all of the red obstacles. In yellow are the sampled failing trajectories found from our STL-based ESS approach. On the left, computed with our STL-based ESS, 0.01% failure rate. On the right, a comparison with Monte-Carlo with 10,000 simulations each, and we do 100 trials each algorithm. We see that in 60% of them, Monte-Carlo did not even find one failing trajectory, and it takes over twice as long to compute, without any optimizations that we can certainly do with our method. We can also use this framework to find a series of measurement noises that causes the stable system and its regulator to exit the initial set in green and enter the unsafe zone, which is depicted with the red hatched box. This brings me to the last slide for today. Let me briefly summarize all of the advantages of our method to probabilistically verify an autonomous system given a specification. Our approach uses ESS, meaning it's rejection-free sampling. The sampling time does not depend on the distribution mass or the probability. We do not even need to know what the trajectories that satisfy the specification look like. We use the STL robustness metric as a measure to decide if the trajectory is satisfying the specification or not, and also to guide the sampling. The fact that we work on full trajectories and that we sample simultaneously from the constrained domains with ESS makes it so that we do not double count events like in chance constraints approaches, or do we have over-approximations. We use parameter-free slice sampling, which is at times even more attractive than optimized algorithms that might be faster, but you need to hand-tune parameters per application domain for it to work well. The fact that we can sample new trajectories and satisfy some STL formula is very attractive for analysis or synthesis purposes. I should also mention that this technique can be parallelized and optimized and have better performance than the current Python implementation. The animation here that you see on the right is from a paper that we submitted to Russ about using this approach for synthesis, but the example also holds for verification. We have a more realistic robot, and we're not only checking the point-to-predicate robustness of the STL, but we can also do this for the polytope-to-predicate robustness. So now the entire robot's body is also accounted for the verification purposes. So now we can verify that the mobile manipulator can perform its task of moving an item in this shelf cabinet. Thank you very much.